So again, threads versus processes. As I basically told you during the last lecture, life is much more complicated than just having like threads and processes, and they are completely unconnected. There are multiple threading models. A multi-threaded kernel is one that allows multiple threads sharing kernel data structures running internally and capable of using privileged instructions. So a multi-threaded kernel is a kernel that it internally has its own threads, and these are kernel level threads. A multi-process kernel is basically a kernel that does not allow having multiple threads in the same process in the kernel. So it's multiple single-threaded processes basically running, and the system calls access shared kernel data structures in this case. Multi-threaded user processes is when each process, okay, has multiple threads sharing the same data structures and isolated from other user processes. So you have different levels of threading model. Multi-threaded kernel, a kernel that internally allows multiple threads to run, and these multiple threads can have a parent thread. They can basically, yeah, they can create threads and create children threads and so on. A multi-process kernel, each process has a single thread and cannot have multiple threads. Okay, and multiple multi-threaded user processes is when the user processes themselves can have multiple threads, and then as life is very complicated, the way that internally the kernel deals with these multiple user processes actually dictate the threading model that you have in your whole system now, not in the kernel. So you can have multiple user processes mapping to a single thread, multiple user threads mapping to a single kernel thread. You can have multiple user threads mapping to multiple kernel threads. You can have multiple M user threads mapping to N kernel threads, and these are all design decisions that you make as an operating systems designer. Thread scheduling, again, it's quite similar to process scheduling. You provide an abstraction of infinite resources to the threads. You schedule each thread to run for some time using round robin, using MLFQ, using whatever you have, and then switch to other threads. Some threads will run faster and might have higher priority. Some threads will be slower. They have IO or they have lower priority. Any multi-threaded program that you're running should be designed to work with any schedule. And by any schedule, I mean that if you do not explicitly say control the scheduling of your threads, which most people do not, then it should not matter which thread runs first, because the operating system scheduler will just pick any thread in random to make it run. So you should not design a program where you have tight coupling between the threads in such a way that, well, if any one of them runs before the other, then you have a problem. So you do not use threading for sequential logic, basically. Threading is for parallel logic, where it does not matter what runs first. Okay? And each thread would run on a dedicated virtual processor with unpredictable and variable speeds. Now, I want you to reason about the execution of these three executions. This is one execution, okay, that is possible in one system. If you look at this at A, what system do you think would run the threads in this way? If you look at B, what system do you think would run the threads in this way? And if you look at C, what system do you think would run the threads in this way?